Good morning. I'm Britton Smith, and I am re-recording a talk that I gave at the YT workshop about PyGrackle, which is the Python extension to Grackle, the chemistry and cooling library. So if you're familiar with Grackle, or not familiar with Grackle, it is a library for doing chemistry and cooling in astrophysical simulations. It will do things like integrate your species or radiative cooling or internal energy given some sort of time step. It will also give you calculations like calculating the instantaneous temperature as a function of internal energy or the instantaneous cooling time or the pressure or the ratio of the specific heats gamma. And the thing that I want to talk to you about today that's relevant to YT is Grackle's Python interface called PyGrackle, which you can sort of see here. So this was implemented by Matt many years ago, and you can do lots of interesting things with it. So you can generate cooling curves, and you can make and run one zone models for evolving at constant density or with a free fall model, so on and so forth. But the main thing I want to highlight here that's relevant to YT is that you can use Grackle calculations as YT fields, right? So I'm going to go back over to a notebook and show you how this works. So I'm going to import NumPy, I'm going to import YT, and I'm going to load one of the primordial star data sets that I used quite frequently in the workshop a couple weeks ago. And I'm going to start from the end of one of those notebooks where I'm going to take a sphere that is about 5 parsecs in size, centered at the position of maximum density. So I'll find the max density, I'll make a sphere there. This is sort of arbitrary, right? And in this simulation, Enzo wrote out the cooling time for all of the cells in the box. And so I will query that here as gas cooling time set to megayears. I'll call that CT0. Let's see what it looks like. All right, so we get values like this, 0.6 megayears, zero 0.9 megayears, so on and so forth. Right, now imagine that your simulation did not write out the cooling time. Well, since that is just a function of the fields that it will most likely store on disk, we can use Grackle to calculate it and essentially access it as if it were a regular YT field, like a derived field. And I do that simply by importing this function, add Grackle fields from the PyGrackle library. And then with that add Grackle fields, I call that with the loaded data set object that I have, see no output. And once I've done that, I have access to fields for all of Grackle's instantaneous calculations. So these are cooling time and gamma, molecular weights, um, pressure, that should be mean molecular weight, temperature, dust temperature, all of these things, right? So I will show this with the cooling time, right? So now this field will be gas, and then it will be called Grackle cooling time. So I'm going to do that again, and I'll query it on the same sphere. And notice this actually takes a little bit of time because this is actually scooping up all the inputs that Grackle needs and then calling this for every grid cell contained within that original sphere. Now I have them, and I can do, for example, the ratio of the values that were saved on disk to the ones that were calculated. And I've put this all in an absolute value here because I know that Enzo saves the cooling time values as the absolute value of the cooling time of E over E dot. And the Grackle ones will give you the raw value, which can be negative if the gas is net cooling and positive if the gas is net heating. So I can do that. And we can see that they're actually pretty close. This is off by about 40%, but some of these are quite a bit closer, right? So this is giving me a reasonably consistent value, but I know, for example, that this simulation was run with, say a different configuration or an older version of Grackle. So this is one way of seeing how things have changed with time, but I'm still getting a reasonably appropriate answer or a reasonably accurate answer. Now, the other thing that you might want to do with this is investigate what the effect of different settings in Grackle would have had on your simulation. So, for example, let's take this thing called CIE cooling, which stands for collisionally induced emission cooling, right? And this is a high density H2 cooling mechanism that happens in densities of 10 to the 12 particles per cc and above, something like that, right? And so in Grackle, this parameter is set with this CIE underscore cooling. But in Enzo, since this functionality pre-existed in Enzo, we call it something slightly different, right? So in Enzo, it's CIE, capital letters, capital C, cooling. I can see what it was for the data set. And this tells me that in this simulation, CIA cooling was set to 1, right? So let's explore what would have happened if CIE cooling had been set to 0, right? So what I'm going to do here is I'm going to create a dictionary of new parameters with the Grackle names, right? And I'm going to set the CIE cooling value to 0, right? Now I will recall add Grackle fields with that same dataset object. And now I will use this parameters keyword argument, and I will feed it in this dictionary of different parameter settings, right? So I'll do that. I'll get all these warnings because all of these fields already existed when we called add Grackle fields the first time. But what has also happened under the hood is that we have reinitialized Grackle's internal data structures with this new setting. So now I'm going to call sp.clearData to clear the cached uh, Grackle cooling time field. So when I call it this second time as CT2, we are going to rerun Grackle and not just take the cached values. And you can see that by it taking a couple seconds to run, right? We'll wait for that to finish. There it goes. And now we can actually see the differences between the cooling time calculation run with Grackle with the parameter settings in the data set versus manually changing the CIE cooling value to 0. We can see that the minimum value, the minimum ratio of these is off by about 3.5%, and the maximum value is, well, significantly less than that, but we can see that there's a change. And Grackle, as you may know, has a couple dozen different parameters. So this is a nice way of exploring the effect of things without having to run an entirely different simulation, or of just retrieving things like temperature or cooling time or mean molecular weight that you may not have stored using Grackle itself, whether or not you actually used Grackle in your simulation the first time when you ran it. So the only thing that this really depends on is having a mapping between your simulation's internal parameters for things and Grackle's parameters. And in general, I would say that it's most likely that your simulation will have a one-to-one mapping between Grackle's parameter names and how you access them in your simulation. In Enzo, this isn't necessarily the case because Grackle's code originally started in Enzo with all these older naming conventions for variables, so we have to have this mapping. But in principle, it's just a dictionary that maps old parameter names to new ones. It can be easily added, and then you can access all of this functionality. All right, that's it. Thank you very much for watching.